Today we're going to discuss the last section of chapter 3, graphs of rational functions and their applications. And we have done quite a bit of polynomials or polynomial functions, polynomial zeros. That's basically the major thing we have done so far. So this section is about polynomial rational functions. So let's just talk about rational functions a little bit in the last section of this chapter. We're going to talk about graphs of rational functions. Okay, mainly. So when we try to graph a rational function, then we have several things to consider. The graph of rational function may have asymptotes. Okay, that's the first thing we discuss. And there are a few types of asymptotes. So we're going to start from the vertical asymptotes. And the curves will have some vertical lines to approach as close as it does, and never touches it. That's called the asymptote. The curve just get closer and closer to some vertical lines, but it never touches it. Okay. But the question is then how to find the vertical asymptotes in this case. Are you still hearing me? I just got a little problem with my internet, I think, or connection of the system for the system a moment ago. So we're talking about the rational function, and by definition is the quotient of two polynomial functions. So let's say f is a rational function, and it is the quotient of two polynomial functions p and q. So how do you know you have a vertical asymptote? Very simple. It says in here, x equal to a is a vertical asymptote of the graph of a function f, provided f approaches infinity or f approaches negative infinity as x approaches a from either the left or the right. Okay, so what does it mean? That's exactly what I said at the beginning. The curve just approaches some vertical lines as close as it is, but it never touches it. So that means the curve just keeps going up or keeps going down without bound. So that means that's what it means by fx approaches infinity or approaches the negative infinity, up or down. Okay. And this approach of the curve to the vertical lines can be either from the left or the right or from both sides sometimes. Okay. So that's how we understand vertical asymptotes in graph. But how do you find a vertical asymptotes algebraically? Okay. Very simple. You just set the denominator q equal to 0 and solve for it. Okay, so to find the vertical asymptotes of a graph of a rational function f equal to p over q, solve for qx equal to 0, but px is not equal to 0 at the same time. Okay, just keep in mind. When you get in other words, when you try to solve the equation of q equal to 0, you get some solutions for x, and then you plug into p, and p should not be 0 when you plug in that solution. Okay. So, for example, suppose we want to find the vertical asymptote of the graph of the function f equal to x cubed over x squared plus 1. So what you do is just set the x squared plus 1 equal to 0 and solve it. But then, we know x squared plus 1 equal to 0 has no real solution, because when you square any number, you get the positive number, or at least 0. When you add 1, then x squared plus 1 will be at least 1 or greater than 1. Okay, so it can never be 0. So there's no real solution for the equation. So that means it does not have vertical asymptote. Actually, if you try to draw the graph, you get something like this. It goes up on the left and goes down on the right without bound. Okay, so we don't see any vertical asymptotes. All right, any questions? Let's do another example. We need to find the vertical asymptotes of the graph with the function g equal to x over x squared minus x minus 6. Okay, so again, you just said denominator equal to 0, x squared minus x minus 6 equal to 0, and then solve the equation. We can easily factor the left-hand side. Okay, so we can that's x plus 2 and x minus 3. Okay, that's the first method to solve quadratic equations, right? All right, you got to find two numbers. You multiply them, you get negative 6, and add them, you get negative 1. So that's 2 and negative 3, right? So then you set each factor equal to 0, x plus 2 equal to 0, you get x equal to negative 2, and you say x minus 3 equal to 0, you get x equal to 3. And when you plug in negative 2 or 3 on the top of g, which is x, it'll never be 0. So that means both x equal to negative 2 and x equal to 3 are vertical asymptotes. So we got two vertical asymptotes. Okay. So in other words, if you draw the graph of x equal to negative 2, you get a vertical line passing to negative 2 on the left, as you can see from the graph. When you draw the graph of x equal to 3, you get a vertical line on the right at x equal to 3. So these are the two broken lines in the graph, as you can see. The function shown in red has 3 branches, 3 pieces. So you can see the curve goes up and down on both sides with the vertical asymptotes, but it never touches the vertical lines. Okay, it just approaches really, really close. And the curve either goes up or goes down without a bound. Okay, so we say they are approaching infinity or negative infinity, right? So there's vertical asymptotes. Well, we've got another type of asymptotes. That's the second type. We call it horizontal asymptotes. So in other words, the curve can also have a situation where it approaches the horizontal line, but never touches it, but it just approaches it, as close as it can be. So these are called the horizontal asymptotes. So we got some horizontal lines for the curve to approach, right? So the line y equal to b is a horizontal asymptote of the graph of the function f, provided the f approaches b as x approaches infinity or x approaches negative infinity. Okay, so when you draw the graph of y equal to b, you get a horizontal line, and the curve just approaches the this horizontal line. So that means if x approaches b, okay, the curve will approach the horizontal line y equal to b. As x approaches infinity or negative infinity, that means this approaching can be either on the right or on the left. If x approaches infinity, that means the graph approaches the horizontal line on the right side. X approaching negative infinity means the curve approaches the horizontal line on the left hand side. Okay. So we're going to see some examples in the graphs you out what it means. So how do you determine horizontal asymptotes again? Then for a rational function. Again, the rational function is defined as a quotient of two polynomials. Let's say the rational function f is a, a quotient of two polynomials, and the top polynomial has degree n. So it's an times x to the n plus n minus 1 times x to the n minus 1 plus everything down to x plus a 0. So that's a polynomial of degree n on the top, and then at the bottom we have another polynomial with degree m. So it's bm times x to the m plus b to the m minus 1 x to the minus n minus 1. I'm sorry, there's a typo here. It should be b n minus 1 instead of a minus 1. A n minus 1, okay. Plus everything down to b1x plus b0, okay. So then, how do you know the horizontal asymptote? Also, we have three different cases. In case one, if the degree of the numerator is less than the degree of the denominator, you just look at the highest power on the top and on the bottom. If the exponent on the top, the highest, is less than the highest exponent at the bottom, then the horizontal asymptote of the graph of f is the x-axis. The curve will approach the x-axis, okay, as its horizontal asymptote. The second case is when n equal to m. That means you got the same exponent on the top and the bottom for the highest term of x. Then the horizontal aspect of the graph of f is line y equal to am over bm. Okay, you just divide the two leading coefficients in the two polynomials. Okay, y equal to n over bm. So that's the second case. So the remaining case is just n greater than m. Okay, so we discussed n less than m in the first case, n equal to m in the second case, and then what happens if n greater than m? The degree of the numerator is more than the degree of the denominator. Then in that case, there will be no horizontal asymptote for the graph of f. Okay, not all the rational functions have horizontal asymptote, just like vertical asymptotes. Okay, sometimes you get vertical asymptotes, sometimes you get horizontal asymptotes, but you don't always get them. Okay, so let's just do some examples. Find the horizontal asymptote of the graph of the function f equal to 2x power 3 over x squared plus 1. So we're trying to find the horizontal asymptote, okay? Not vertical asymptote. So what they do, you just compare the highest exponent on the top and at the bottom. So what is the highest, largest exponent on the top? 1. So x to the 1, right? That's the highest power term. So n equal to 1. What is the highest term in the denominator? X squared. So m equal to 2. That's the highest exponent at the bottom. So n equal to 1 equal to 2. So n less than m. So according to the rule, the x-axis is the horizontal asymptote. Okay, when n is less than m. That's what it says in the theorem on the last page. So if you draw the graph, you can actually see the curve is like this. You can see the curve actually approach the x-axis from both ways, both on the left and on the right. Specifically, this function approaches the horizontal axis from below, and approaches the horizontal axis from above on the right. Okay. on the left, they just approach the horizontal axis um, from below, right? On the left. Okay. So that's one example. Let's do another one. Find the horizontal asymptote of the graph of the function fx equal to 4x squared plus 1 over 3x squared. So this time, again, you just find out n and m. So n is equal to 2 x squared on the top. That has the power term. Then also we got x squared at the bottom. So m is also equal to 2. That has the power in the denominator. So they are the same, n equal to m. So according to the theorem we just discussed, the function has horizontal asymptote y equal to an over bm. So you just divide the coefficients of those two leading terms on the top and at the bottom. Okay, when the two exponents are the same. So on the top, the leading coefficient is 4, and at the bottom, the leading coefficient is 3, so we get 4 over 3. So the horizontal asymptote is y equal to 4 over 3. So if you draw the graph of y equal to 4 over 3 is a horizontal line passing through 4 over 3, on the y-axis. So as you can see, the broken lines in the graph, and the curve, as we see, of the function in red. So it has, it does show the asymptote for that horizontal line y equal to 4 over 3. Okay, both on the left and on the right. Okay, and both approach the horizontal asymptote from above. And you can also see there's actually a vertical asymptote, which is the y-axis, right? So in this function, it has both horizontal and vertical asymptote. Okay, in the previous example, it does have horizontal asymptotes, but not vertical asymptote, right? Okay, so everything can happen. So how about the next example? I find the horizontal asymptote of the graph of the function f equal to x plus 1 over x minus 2. So again, to find the horizontal asymptote, you need to compare the exponent, the highest on the top and at the bottom. So we get x cubed plus 1, so the highest exponent is 3 on the top, so n equal to 3, and x minus 3 in the bottom, so the highest exponent is 1, x to the 1. So m equal to 1, so that means n greater than m. According to the theorem, it says the function has no horizontal asymptote when n is greater than m. Okay. So the graph is showing, on the right, as you can see, you don't see any horizontal, right? Okay, so that's this example. Any questions? Okay. I think I do got a little problem with the camera, maybe the internet then. Okay, so we talk about both the horizontal and the vertical asymptotes, and there is another asymptote we talk about as called slant asymptotes. All right, and this kind of asymptote is a line not neither vertical nor horizontal. The curve just approaches a line neither horizontal or vertical. Okay, so it's called a slant asymptote. So how do you know there's a slant asymptote of the rational function? Okay, again, you just take the quotient of two polynomials to get a rational function, and when you do it, the quotient you get, okay, it gives you the slant aspect, but that only happens, okay, when the degree of the top polynomial p is 1 greater than the degree of q at the bottom. So you need to look at the highest coefficient, has the exponent on top and has the exponent at the bottom. See if the difference is 1, okay. If that's indeed the case, then you're going to get the slant asymptote, okay. So let's just do one simple example. Find the slant asymptote of the graph of the function f equal to 2x cubed plus 5x squared plus 1 over x squared plus x plus 3. Okay, so first, look at the degrees of the polynomials on top and the bottom. Okay, we see 2x cubed that has the power term on the top, so the degree of the top polynomial is 3x cubed, right? And similarly, you look at the bottom polynomial x squared plus x plus 3, so the degree of the bottom polynomial is 2, x squared. Now, n equal 3, m equal 2, so the top polynomial has degree 1 more than the bottom polynomial, right? 3 minus 2 equals 1, or n equal to m plus 1. Okay, so in that case, then we do have a slant asymptote. So what you do is you just take the division. You do the non-division in this case. I hope you can still remember how to do the non-division. We discussed at the first section, the very first thing we discussed in this chapter. If you do the non-division, just like you do the division of numbers, by the way, you're going to get the fx equal to 2x plus 3 plus negative 9x minus 8 over x squared plus x plus 3. So we got the quotient of 2x plus 3 from the result of this rational function, and then obviously there is a remainder of negative 9x minus 8, but that's not our focus. We just interested in the quotient of 2x plus 3. So in this case, the graph function has slant asymptote y equal to 2x plus 3, just the quotient. Okay, so if you plot the graph of y equal to 2x plus 3, you do get the linear function. And if you draw it in the graph, you can get a line of slope 2 and the y-intercept 3 in this case. So in showing the graph, we see the slant asymptote in broken lines, and then the curve in red. So you can see the curve does approach the broken line, on both ways in this case, actually, right? It approaches the line but never touches it. So what's the point of those, discussions of asymptotes? All right, it tells you the shape of the curve on the ends. Okay, for example, in slant asymptotes, then you can see the curve will behave pretty much like the line, on the top and at the bottom, far away from the origin, right? It's like a line, okay, with that slope. Slope 2. Similarly, in the case of vertical or horizontal asymptotes, you can see the curve just looks like pretty much a vertical line or horizontal line, either on the top or bottom, or left or for right, So this does tell you some features of the curve on the graph, right? So that's the end of this section and the end of this chapter. All right. So and let me just stop the recording.